Okay, so now we jump ahead to the 1800s. So we started 2,500 years ago, and now we're just in the 1800s. So like 200 years ago.
Yeah.
Yeah. And actually, a lot of very famous mathematicians worked on this problem. And the proof, or the name of this, is the prime number theorem. And what this theorem says is, or answers the question, about how many primes are less than
A number?
than your number. So, and the Belgian mathematician and the French mathematician Hadamard, and the Belgian mathematician whose name I'm not going to be able to say well, Vallée-Poisson, proved that the number of primes less than a given number is approximately x divided by log x. So I have to tell you what log x is.
Mm-hmm.
You remember what log x is?
I think it's like if you have a number, it's the power.
Okay, so we're used to, or one common way is log base 10 of a number.
Yeah.
And this is approximately the number of digits. Okay, so like the number 123 has 3 digits, so we would say the log is about 3. Okay, this isn't a precise definition, obviously. Yeah. What you're remembering is it is exactly 10 to what number y equals 123. We know 10 squared is 100, 10 cubed is 1,000, so it's somewhere between 2 and 3.
Yeah.
That's what you're remembering. Mathematicians like to work with a different number instead of 10. They like this number, e.
Yeah.
Do you know about e?
Yeah. Euclid found it.
Not Euclid.
Euler.
Euler, yeah. Log base e of x answers the question, e to what number equals x. Okay. And e is about, you know?
It's 2.71828 about.
2.718. Okay. And so what we could really do is say this is approximately the number of digits times 2, roughly, because e squared is close to 10, because 3 squared is close to 10.
Yeah.
Okay. So this is actually pretty interesting. So now we know, in the 1800s, we know more. We know not just that there's an infinite amount of primes, we can actually sort of count them.
Cool.
So for like the number 10,000. Okay, so the number of digits
is 5.
5. And then we multiply that by 2 to get 10. So we would expect there's about 1,000 primes less than 10,000.
Wow.
Now, if I would have planned ahead, I would have checked exactly how many there are, but we can check when we're done.
Yeah.
Okay? Or for a really big number, like 1,000,000, same thing. How many digits?
There's 7.
7. So times 2 is
14.
14. So 1,000,000 divided by 14, whatever that is about the number of primes less than 1,000,000.
Wow.
So for numbers up to 1,000,000, about 1 out of every 14 is prime. For numbers up to 10,000, about 1 out of every 10 is prime.
Cool.
Okay? So you can see from that primes sort of get less frequent as numbers get bigger.
Yeah.
Yeah, because I'm taking the number of digits.
Yeah, and as there's more primes, that means the numbers that would be primes are divisible by those primes.
Yeah, that's right. That's right. That's a very good observation. As numbers get bigger, you have more primes underneath them that they might divide into.
Yeah.
So that's another reason why there's fewer and fewer. You can think about the sieve of Aristophanes. You're crossing out. You have more and more numbers that you can cross out.
Yeah.
Okay, it's pretty neat, right?
Yeah.
So this was a big step. So Euclid showed there's infinitely many, and these guys, plus some other really famous mathematicians, showed that here's about how you count them. And they showed that also about how they kind of spread out as you get bigger.
Yeah.
And that led to some people wondering some pretty interesting questions. For example, for a given number, how many primes divide into it would you expect? Okay, number 1. And number 2, since the primes spread out, you do have some primes like 3 and 5,
That are
5 and 7, 17 and 19, that are right next to each other,
they're twin primes.
called twin primes. And people wondered, are there infinitely many twin primes too? Because as the primes spread out, as the numbers get bigger, maybe they spread out so far that you just stop having primes next to each other. Okay, people wondered about that. You ready for the next step?
Yeah.